Thank you very much for giving me the opportunity to talk about this work, which we have been doing recently on tungsten telluride. So I can immediately jump to the slide of the team. So we have used tungsten telluride crystals, which were grown in the Mandrus group, and by these persons you see on the slide. We also use boron nitride to encapsulate the material. I mean, one cannot give enough credit to these both persons here, because almost all graphene work today relies on the quality of this boron nitride material, which they provide essentially to the whole world. And then in my group, the people that contributed to that work is mostly Artem. So he should actually give the talk here. Artem Kononov, he's been starting this work in collaboration with some others. Gülbostan is left, and Martin has also been involved strongly in that. Okay, so funding, we have the Artem is paid by some special private funding, George Andres postdoc cluster, and then we have ESC grant and Swiss National Science Foundation and SNI. Okay, so maybe quick motivation for me personally. So I'm interested, we are in our group interested to engineer topological superconductors, starting with 2D van der Waals materials like graphene, and then combine this with superconductor, induced superconductivity by proximity effect. And there's one example very recently been showing in this paper here from the group of Benjamin Sassepe, where they actually showed if graphene is very clean and sitting on strontium titanate, which screens interaction, then one can get in the lowest lambda level and get or the lowest state split, value split, and then form edge states naturally. Like you naturally can get a helical system in this material without field. They shown this kind of a plateau of this helical state. It's still not perfect, but there is quite some evidence in that work for possibility to even engineer a helical state in graphene alone. We ourselves have been working more on 2 layers of graphenes, where like this system, double layer graphene system, which are not tunnel coupled in this sense, but in magnetic field at the lowest lambda level. If you dope the upper one to the electron side and the lower one to the hole side, then you have counter-propagating edge states which carry opposite spins. So this kind of a synthetic or engineered helical system, which we then like to couple to superconductors. We have been working on this intensively. So I recently published a paper where this was done mostly by this person, David Indolese, where he could stack 2 graphene layers encapsulated in boron nitride and even coupled to a superconductor has been realized. I haven't seen yet topological superconductivity in that material yet, but it's underway. Okay, then there are been other examples in the literature, for example, bismuth and niobium to induce proximity effect. And then bismuth crystal phases has some helical hinge states, which can carry then with superconductivity lead to Majorana states. Other proposal longer ago is shown here down here to start immediately with a topological insulated material and combine superconductivity therein. So along this line, so we started to work on tungsten telluride, which is a topological insulator in case of monolayer. So here's kind of an overview of this. So bulk crystals are type 2 Weil semimetals, and in the monolayer it can be a topological insulator with helical edge states. There's some experiments on this in the literature. And more recently, there's also been suggested from some theory work that tungsten telluride could be a second order, higher order topological insulator, which carries states at hinges. Right? So from the superconductivity is also interesting in tungsten telluride. So if you can realize this, let's say, helical system states, then also superconductivity is not far away. So people have shown on the high pressure superconductivity by doping, and also monolayer can be gate tuned into a superconducting state. So by this, you can probably get both in the same material, so you induce superconductivity and having helical states, maybe give then rise to topological superconductivity. Okay, so this is the motivation. And when you use what we are doing, we are people that do electrical transport measurements, so measure currents make devices. And then one important thing is you want to know whether there's current flowing in the edges. So we are interested mostly in determining current distributions in such materials, and that can be done in Josephson junction here. And that's one important experimental approach to get information about current distribution. I'll just explain a bit more, but there's another ingredient which one is also important if one measures this. If one tries to measure current distribution, one should also be aware that there is a current phase relation of Josephson junctions. And normally in textbook, you know, a simple tunnel junction has this sinusoidal current phase relation. So there's a critical current here, and this is the current, it's a function of phase, depends on sinus. But it's only true for weakly coupled tunnel junction. So it can be looking more complex. I just showed this just as an illustration. This is how it looks like for a system which is a diffusive coherent system in a short junction limit. Okay, so it's non-sinusoidal in general, particularly if you have highly transmissive channels, like, you know, a helical edge state or so. There are some nice papers which came out recently also in transport by Helen Bushia's group using bismuth nanowire. So this is bismuth wire, and here's a test experiment where they make a squid loop, a DC squid loop with a reference junction, and then looking at, you know, then if you measure essentially conductance through such a system, it will be periodically modulated, the critical current, and you see something. What you see here is essentially kind of a current phase relation, and you see this non-sinusoidal, and this is exactly what it has. The shape it has now is very skewed, we say. It's forward, it's like triangle, looks like triangle, it's 2 pi periodic still, but it's definitely non-sinusoidal. So one has to keep this in mind, because in this analysis, which I just described in the following, the assumption is made it's sinusoidal. So what people usually do, or we also do, we take a sample which has some 2D material where current can flow in the plane, and if the current would flow between 2 superconductors, Josephson junction, say homogeneously, then when you apply perpendicular magnetic field, there's a phase gradient appearing. This is the phase here, the phase gradient in the y direction, and yeah, we have to you sum up all this contribution to the supercurrent with the phase to get the total current, and then this, because of this, yields due to interference now in the magnitude of the critical current, a pattern which you know is known as a Fraunhofer pattern. It looks like diffraction from a slit in optics. So that's how it would look like. Maximum critical field at zero, maximal critical current at zero field, obviously, and with field it decays away with this pattern. And if you only would have edge states, helical system only, no bulk current, then you would have 2 channels interfering, and it gives a kind of squid periodic oscillation, squid type signal, we call this. From the periodicity, you can say something about the area, which this one flux quantum in this area gives one periodic in this signal, one period in this signal. Okay, this is for the start, and then there has been papers, very nice paper has been done on Mercury Telluride by Jacobi and Molenkamp group, and that's an example where you can see exactly this. So in the top measurement, this is the Fraunhofer pattern. Critical current is a function of perpendicular magnetic field. It looks Fraunhofer-like, and then it turns out that if you kind of go back to the current distribution by simulation, you see more or less homogeneous current distribution. While here is very much squid-like. I mean, it's still a decay, but it's it's much slower decay than what you see here. That indicates edge contribution. Now, okay, so we use tungsten telluride crystals. They will be exfoliated and then encapsulated with boron nitride. And actually, in our devices, we use palladium contacts. To show you an example, maybe it's easier. So the palladium contacts are fabricated first, and then the boronite, the tungsten telluride with the boron nitride is put on top. So actually, the tungsten telluride is the darker bluish thing you see behind here. It's kind of a strip here lying under this bigger contact. And this, I indicated here the border. This is a bornitide, which sits on top, and the contacts are below the tungsten telluride. Now, there's a first measurement here. It's kind of a Hobart type experiments. You pass current from the outer contacts, measure the voltage drop here on the side. And this is at higher temperature, and it shows this strong positive magnetic resistance, which is kind of characteristic of a good, it's believed to be characteristic of a good wire semi-metal material. So it's not the monolayer we look at here. So we've studied a few layers of tungsten telluride, so that's maybe in the range of maybe a few 2 to 7 layers or something like this in this range. You have to think about. So the same sample, now we go colder in temperature. Now it's going to look like this. It's the same measurement. We measure here the resistance, the 4-terminal, we call this the longitudinal resistance, RXX. And now you see when you go to low temperatures, or the lowest temperature is the blue curve, and this functions magnetic field. And you see if you go to zero magnetic field, actually it's zero resistance state. So there's something superconducting now. But it's not as easy as you think, because there are two transitions. So there's a transition here. You could say this is the critical field for one transition. It's about the Tesla, a little bit more. And if you go to say if you go to very small field, you ask question, what would be the transition to the zero resistance state for very small fields? Then you see that the TC is around maybe a little bit. This is 1.1 Kelvin, so still dips down a little bit. So there around is the TC between 1 and 1.2 Kelvin. So this drop is actually, our interpretation of this is that this is an induced superconductivity in tungsten telluride, so the tungsten telluride becomes superconducting. But in our case, we also have to get the whole junction superconducting. So I just show you a picture afterwards to explain this. And the similar thing you see in the critical current. You see these two transitions here, one is around here and one is up here. And they correspond to two different physical properties. So the explanation is coming here in this picture. So what we think, what happens is the palladium itself induces contact is from below, induces superconductivity into tungsten telluride, into a thin crystal with a TC of around 1 or 1.2 Kelvin. And then, so this will be zero resistance state here. But since we measure, there's still a distance, half micron or a micron in between. If this is too long, there will be no supercurrent flowing. So this you can view as a Josephson junction now. And so we need some Josephson coupling. And this sets in at lower temperature. So at lower temperature or lower magnetic field, you see the dip going to zero. And this dip here is the formation of the Josephson junction. Okay, so now, well, this may be not too surprising that we can induce superconductivity from a normal metal contact, palladium, because also people have seen that the electron doping itself can induce superconductivity. And maybe there's also interdiffusion that may play a role and produce some kind of superconducting material here. But the details, we don't know really what happens, but we're quite sure, about the superconductivity which is induced. That's very well reproduced in more than one sample. Now, if you look more careful now here, right, what's actually in critical current measurements. So we're going to look at current measurements next. And that's shown here at small magnetic field. So now you see that you have to think about now, this is an extended sample. I've shown you this Fraunhofer squid pattern, remind you about this picture here. And you see that there's something, on a larger scale, this one. It looks a little bit, maybe some wiggles here, a little bit more like this, on a larger field scale. But as on a very small field scale, a very strong squid type, pattern like this one, overlap. And this small field, this below millitesla, indicates a large area. So actually, I indicated now with these dotted points here, where we think that the current flows along the edge of the sample, and this is the large area which would be consistent with the periodicity we can see here. So it looks, you could say, oh wow, we see now edge current, and it's flowing over, over the whole sample. and gives rise to the squid signal. But one has to be a little bit careful, because you also have to see that in this particular first devices, we made the contacts just very, touching from the side. There are a little overlap here, and if there is a doping induced, change in a band bending or something like this, then it's obvious that if you inject current only at the edge, that most current may flow at the edge. It's just an artifact from the way we made the contact. So that's not yet the full proof. So in the next samples, Artem fabricated contacts all the way through all the way across the sample. So the greenish part is the tungsten telluride. It's also sitting. I mean, the palladium contacts also sitting below that tungsten telluride, and this boron nitride crystal on top, and which is keeping the oxygen away from the tungsten telluride. So here there are several junctions now. You can measure the voltage drop, for example, from here to here. This is a short junction. From here to here, it's also a short one. These are micron wide, and this is 2 micron, and the other ones are larger here. They're further apart. So on the right side is a measurement shown for the critical current. For actually V1, this is a short one. V2 is a short one, both 1 micrometer long. And then number 3 is like a bit longer, 2 micron. So in the 2 micrometer long one, this is at the lowest temperature we can measure. In the dilution fridge, a small dip appears. Maybe it's a precursor, but there's clear supercurrent in the 2 junctions, 1 and 2, of a distance of 1 micron. And now again, we can do the same thing, the same game, apply small perpendicular magnetic field, and see how learn something about the current distribution. And what we see, this is shown on the left here, for the 2 junctions which are 1 micrometer wide. And you see this, the peak in the center still has some Fraunhofer contribution. But again, the squid signal is very, very, it's very impressive how many periods you see this oscillation. So the squid is decaying very slowly. And that means that the current flows over a very, very narrow region. Now, one can try now to analyze this according to what people do in literature. So there's a method proposed by Fulton a long time ago. So you start to get this, the idea about this Fraunhofer pattern starts from the point that you have a current distribution as a function of along the width of the sample where the phase gradient is. And now you write it with an amplitude and with a sinus here in this function. So when you start to write it like this, you already assume it's a sinusoidal current phase relation. And then you have this phase gradient in with this x here. And since this looks like a Fourier transform, right? And so at the end, you have to look at the maximum of, the critical current is the maximum of this expression where you vary the phase. And now the question is, when you measure this here, the critical current as a function of magnetic field, can you sort of like or can you back convert to J of X? And obviously you lose some information because you take here the magnitude of this, so it's not directly clear it's not that the mapping backwards is not 1-to-1. So it has to make some assumption when you when you do the back transformation. And in particular, actually, it assumes that the current goes to 0 at the places where there is destructive interference. And you can see this is not the case in none of them. So one has to always take this. This is the analysis actually, trying to to invert this functional to get the critical current as a function, or the current distribution as a function of X. One has to take this with some cautious and grain of salt or so. But what we get out is there's obviously some bulk contribution. That's also obvious from this larger middle peak here. But there's a very large part of the current flows along the edges, and on a very narrow scale. So, I mean, it must be narrower than 80 to 70 nanometer. That's the resolution we get from the number of periods we can see. So there is indeed edge current, although these junctions are now right, the contact is over the whole width. We see essentially only current flowing at the edge. Most current flows at the edge. Now there's a control experiment done. There's another tungsten telluride crystal, as you can see here in bluish, and it has a step. It's actually 2 layers in the outer region and 5 layers in the darker middle part. And there we made the contacts a little bit different. We made a gap in between. And our idea was to be able to do some quasi-phototerminal measurement. So we thought, check the current here, then flows like from left to right. And here we can essentially measure the voltage drop. But we were not, this was not a good idea, because the small slits here, that even gives Josephson coupling, so the current can also flow through this junction here. And then if there's edge current, it can also flow backwards, it could flow like this. I mean, in some very crazy pattern here around this sample. That we then only realized once we did the measurement, that this was maybe not as clever idea, but it gave still some interesting results. So the experiment, let's look first at the critical current in no magnetic field for junctions that are the different lengths also here, shorter ones and longer ones. So it's micron, 2 micron. And again, you see 1, 2, 3, 4 micron. And in the 2 micron, or even the 3 micron in the blue curve, you have a critical current here. It's dipped to 0 here. This is also up to 3 micrometer, we see supercurrent. And then it's more pronounced. Critical current is larger for 2 and for 1 micrometer. It's almost a 4 microamp. One can then also calculate the IC and Rn product. Rn is the resistance and in the normal state. And we get quite large values, which is a sign of ballistic, we're close to the ballistic limit. Okay, now the measurement with magnetic field, so it's perpendicular magnetic field. Unlike before, it is now a large scale, right? It's like 1 Tesla, 2 Tesla. And you see for the different samples, so let's maybe the red one or the black one, these are the shorter junctions. You see the decays, and then you see it has some humps here, particularly good visible in the red one on a large scale. But if you go here and zoom, blow this scale up, right? It's done in the inset. You see it's again millitesla scale. It's 1,000 times less scale. blown up, and you see there's a fast oscillation due to. This is due to edge current, which is flowing in this sample. So we see the fast oscillation corresponds to a large area. And now actually from this, we figured out that, for example, such a junction here, which we thought maybe when we inject current here, current would only flow in this area here, essentially, but current can also flow in bigger areas because this is a Josephson junction. Each edge you can view as a Josephson junction. And actually it turns out, if you try to find what period fits both best to the geometry of the device, and we assume in 2 layers, it's actually known that there are no edge current from previous literature, that indicates that the edge current is flowing actually on the step edge from 2 to 5 here. So that's giving the main period, like some areas like this here, giving the main period in this sample. So there's now some evidence from edge current, on step edges. Maybe these are of hinge type. Maybe this is kind of what we speculate here. And but in addition, there's a slower oscillation. So the slower oscillation on a scale of, maybe 1/3 of a Tesla indicates a very small area, and that's what we propose here. That will fit pretty well. So if you would think that from 2 layer to 5 layer, this is not the step. There's some kind of shift maybe in the next layer, in the 3rd one, so of a small distance here, and then we might get supercurrent in different position, different layers here. Then if you would assume this here for the junction, it would mean that W is 5 nanometer. It's pretty short. So we cannot assign it to this split opening. It's too small, but it's this could be fitting very well. We don't know whether it's this, but well, that's what we propose. Now there's something in the literature which looks almost similar to what we've been looking at. This is This is in bismuth nanowire from the Bouchard group. They see also a fast oscillation in the critical current and something more slower. And their interpretation is kind of a bit different. So the fast oscillation is a big area going. There's some edge current on hinges. So this big area and the slow the oscillation on a large field scale, they interpret it as a spin Zeeman term, and that's also a possibility. So there's a Zeeman splitting, and if there's only a few channels, so let's say one channel, there is no dephasing, and you see then the periodicity appearing from the phase shifts due to the two spin bands. That could also be an explanation of what we see here. So we don't know exactly of whether it's this something like this, or whether it has a origin from spin Zeeman terms. Okay, we also find something in addition. We find some asymmetry. The Johnson effect is asymmetric. That means if you measure the critical current in the, say plus means in the positive direction, and you measure it in the opposite direction, then this was always hold. So if you would measure the current in a negative direction, but at negative field, then you reverted the time. Current flows backwards, but also the magnetic field is backward, then this should always hold from time reversal symmetry. Now, if you break some other symmetry, like inversion symmetry, then in this recent paper, it has been proposed that they call this the asymmetric Johnson effect, that also other symmetries which we usually see or think to see is that the critical current as a function of magnetic field is the same for positive current and negative current, which is usually assumed, and the same for positive and negative magnetic field. But in this calculation here, actually on this green point line, this is a positive current, this is the negative current. And here it seems to be, just the negative of it, the same magnitude. But if you are here, it has not the same magnitude. So this symmetry would be broken. And they do some calculation about this for Weil semimetals. And that somehow due to Fermi arcs and so on, due to some asymmetry terms, they can reproduce some asymmetry in this current, critical current as a function of magnetic field dependence. Now, actually, we see this in the experiment, very, very pronounced. These are two samples. Maybe the most pronounced one is the red and the blue. So the red is sample 1, current positive, magnetic field positive. And here we revert the current to the opposite direction. And to show on the magnitude scale, we change the sign here. So the blue and the red, they don't overlap. So they break this kind of symmetry, which one might naively expect. If you change also the magnetic field, the sign of the magnetic field here, right? Then they must overlap. And you see that both overlap, both samples perfectly overlap. And so it just shows that fundamental time reversal symmetry is still there if you change also the direction of the field, obviously. But one has to be very careful with this analysis here. I mean, although our sample shows an asymmetric Johnson effect, one can easily show that if the current phase relation is not sinusoidal, if it's non-sinusoidal, it will also become asymmetric. So if you see the asymmetric Johnson effect, I mean, you cannot claim. I mean, you cannot say this is a proof for, for having some kind of edge current of topological origin. Now, there's also, now I have to see my time. Let me see. How is my time? Should I finish now?
Well, now it's 5 more minutes.
There's no problem. Yeah, then I can quickly go through that. We can also find can also ask this kind of, very interesting that you can induce superconductivity from a normal metal. Lead. And the question is, can we say something about this induced superconductivity? Is it special? And it turns out that it's a little bit special. So before we are concentrating all on this is when the Johnson current flows, when you have Johnson junction. Now we concentrate on this drop downwards here, where essentially the contacts get superconducting, and look at the critical fields. And this plotted as a function of temperature here. And it follows, as expected, the 2D Ginzburg-Landau equation, which should be linear. And you see from this equation that you can deduce the Ginzburg-Langnau coherence length. It's pretty short. It's 40 nanometer. And from that, you can get Fermi velocity. I have to make some assumptions. So this is kind of in the clean ballistic limit. But you can also put mean free path is not so large. You can also put the mean free path in. This will not change this equation much, maybe a factor of 2. So what we get out is a very small Fermi velocity. That's already strange. I mean, it's quite low. And now we can do one more. We can also deduce the London penetration depth. So if you do these experiments where you put perpendicular magnetic field on the Josephson junction and try to look at this Fraunhofer type physics, I didn't say anything about this. I just assumed that the field would be in the gap, but the field also penetrates the superconductor to some extent, given by the screening length. Now this screening length in 2D, this we can measure from the experiments. It's about 400 nanometer, and one can relate this. This is a special. The normal 3D London penetration length is here, and the thickness of the sample also enters. So you get the London penetration length of about 50 nanometer, puts the superconductor in the class of type 2. But when from the London penetration depth, and you can also get essentially the carrier density, the density of state, the density of state in the material, and also the carrier density, and it's pretty large actually. These are estimates for the density of state, and it's very large. So I mean, it's kind of a hypothesis. So almost a small velocity, high density of state points to some flat regions in the band. So questions, could there be some flat band superconductivity? So I don't want to claim it is flat band superconductivity, but it could be something like this. Now, people have seen that strain can, strain at the interface maybe can induce superconductivity. The doping, maybe there's some doping which is transferred from the palladium into the tungsten telluride. And another interesting aspect is we also exceeds the Pauli limit easily, certainly in parallel magnetic field. So this is now parallel magnetic field, the same thing. So this is the critical field here, it's plotted here, the red curve. And it goes up in parallel magnetic field almost up to 1 Tesla. So maybe the most likely case is that there's some doping effect from palladium that is inducing this, but that needs further studies. So that brings me to the end. So we studied Josephson effect in few layers tungsten telluride. We found supercurrent, strong contribution from edge current of narrow size. The current can flow up to 3 micrometers. It's also quite large, long distance. 1D states can reside on the edges and possibly what we have seen also in steps. And Josephson effect shows this asymmetry effect, and the supercurrent can exceed Pauli limit. That's all. Thank you very much.